Welcome to this video. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is August 7th, and the title of this lecture is DC Parallel Electrical Circuit Analysis. In this lecture, you will learn how to calculate the variables involved in a direct current parallel electrical circuit. DC parallel electrical circuits maintain constant voltage while allowing for current draw by means of resistors. In a basic sense, in regards to analog DC parallel electrical circuits, physical resistors are present which can be installed and removed by means of soldering and desoldering for repair or customization purposes based on required resistor ohm specifications. However, in the present day, DC circuits are not analog circuits but are digital circuits which contain operational amplifiers, MOSFETs, programmable logic circuits or PLCs, and digital wireless interfaces allowing for programming to change resistor specifications without actual physical interaction of the circuit. Digital signals processors, crystalline CPU, and PLCs allow for software control of DC parallel electrical circuits. Values then quantified using binary base 2 logarithm mathematics instead of decimal analog mathematics. Regardless to how advanced DC electrical circuits become, they are still bound by Ohm's law. Now let's proceed to two DC parallel electrical circuit analysis problems. Here we have a purely parallel DC electrical circuit which has a source voltage of 24 volts DC. This DC voltage could be from an AC to DC rectification diode or a transformer AC to DC application like a wall plug-in rectification and transforming from AC voltage to DC, including a step down, or this could be coming from an engine driven alternator converting AC power into DC power by means of a diode and a voltage regulator. Whatever the DC power source, it's identified with a positive and a negative, because with DC, direct current, electrons flow from positive to negative, only in that direction. Since this is a purely parallel circuit, all the functions are parallel. We don't have any resistors in series or in between the resistors, so the voltage is going to remain constant throughout the whole circuit. The voltage that is flowing through all four of these resistors will equal 24 volts because it is a parallel circuit. What we need to know is the total resistance involved in the parallel circuit here, and that is accomplished by using the inverse sum rule, or the inverse summation rule, in regards to resistors in parallel, which you cannot add together like you can with series resistors. You can add them together, but in parallel circuits, parallel DC circuits, in regards to total resistance, you have to use the inverse summation rule, and you do that by taking 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, on and on, as many resistors as you have. If you have just two, let's say we didn't have these two, you can then take the product sum rule and multiply the 8 times the 22 and then divide it into 8 plus 22, and that would allow you to get the total resistance of two resistors in parallel. But since we have more than two, or say 3 or more, you can use the summation rule, which is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, and then you can calculate the total resistance in regards to resistors in parallel, which you cannot add together like you can with a series DC circuit when the resistors are in series. So the purpose of calculating the total resistance of this given parallel DC electrical circuit is so that we can calculate the total current. And Ohm's law is E, which is equal to voltage, is equal to I, which is equal to current in amps, times R, which is resistance in ohms. So once we calculate the total resistance, we can then solve for I. I is equal to E over R. We can take the total voltage, divide it into the total resistance to get the total current. So right away, if we look at the questions we need to ask to understand the circuit, we have total voltage. We can use inverse summation rule to get the total resistance of resistors in parallel. Then that allows us to calculate the total current, and then the voltage drops across all four resistors will be equal to the source voltage because we don't have any resistors in series dropping that voltage. So all four of these will be 24 volts. Yes. Now to find the current at the resistor, again it would be Ohm's law. I is equal to E over R. So we could take the voltage 24 and divide it into the resistance 8 ohms to get 3 amps, and then 24 divided into 22, whatever that is, amps, and so on and so forth. So that would get the current at the resistors 1 through 4, and then power is simply P equals electrical power DC is equal to I, which is amperes DC, times E, voltage, which is DC volts. So you take the DC amps times the DC volts to get the DC power in watts. So you could simply just take 24 times the current you get at R1. So in this case, 24 divided by 3, or 24 divided by 8 is 3 times 24. That would be the watts at resistor 1. You can repeat that. Now I'm going to show my work down here, explain this so that these questions can be easily answered. So again, we use the inverse summation rule, 1 over 1 on the numerator, 1 divided by the denominator, 1 over R1 times, or 1 over 1 divided by R1 plus 1 over R2, and on and on and on. So in this case, we fill in the blanks. We can check that. So 1 over 8 plus 1 over 22 plus 1 over 35 plus 1 over 65. That's what we have here. When we calculate that out, the total resistance is 4.66 ohms. So we got total voltage divided by total resistance. So total current is 5.15 amps. The voltage drop across resistors 1 through 4 are all 24 volts because it is parallel. The voltage stays constant. There was no resistors in series in between those parallel circuits to drop the voltage, so they remain constant. And then current at resistor 1, again, that is solving for I in Ohm's law formula. So 24 volts divided by 8 ohms at resistor 1, so 3 amps at resistor 1, 1.09 amps at resistor 2, and on and on. Now, the last part is the power dissipated at resistor 1, so we would just take the amps we calculated at resistor 1, 3 amps, times the volts at resistor 1, 24 volts, so 3 times 24, 72 watts. Same thing, there's 1.09 amps at resistor 2 times 24 volts, so 26.16. 0.69 amps at resistor 3 times 24 volts, 1656 watts at resistor 3, and the same process here for. So we then take the total current and multiply it times the total voltage. We get 123.6 watts total power in this given circuit. And to check our work, we can calculate on a summation, adding together cumulatively the power at each resistor being dissipated. We can add those together, and if you did it correctly, that should equal also 123.6 watts total power. So when we add them all, add the power dissipation at each resistor up, we do get 123.6. So this circuit analysis has been proven is correct. Here we have another DC parallel electrical circuit. Remember, the electrons move from positive to negative only. In this case, we have a switch that is opened and the circuit shut off, de-energized, and then when the on-off switch is actuated, turning on the circuit, this closes the circuit by grounding the switch, and then it causes the electrons from going from positive to negative to go switch to ground and then back into the battery's ground itself, completing the circuit. So again, just like the previous problem, we have to answer these questions, and right at face value, since there's no resistors in series in between the parallel circuit resistors, we know that the voltage is going to be constant throughout the whole circuit. So all of these circuit resistors will have 9 volts. Now we have to do the same inverse summation calculation to find out the total resistance of resistors in parallel. So we go 1 over 1/8 plus 1/6 plus 1/14 plus 1 over 0.5 plus 1 over 2, whatever that equals. That is the total resistance of the circuit in ohms. We have the total voltage in volts. So we take the total voltage and divide it into the total I is equal to E over R, so total voltage into total resistance. That will calculate the total current of the circuit. And then from that point on, we can go and use Ohm's law again to calculate the current at the resistors. We know the voltage drops across all the resistors are 9. And from that point on, we can get the power, just like the last one. So once you get the total resistance, it gets pretty easy after that. Same process. Draw 1 and then a fraction sign, and then underneath the fraction sign in the denominator, then it's 1 over 8, 8 ohms, 6 ohms, 14 ohms, 0.5 ohms, 2 ohms. So when we make this calculation, it's 0.35 ohms total resistance. To get the total current, it's the total voltage into the total resistance. That's the total current, 25.7 amps. And then of course the voltage drops across all the resistors are constant because there was no resistors in series between the parallel resistors. So there's no drop in the voltage, it's parallel. And so 1 through 5 I'll have 9 volts. And then to get the the current at resistor 1, again, where it's I is equal to E over R, so E, 9 volts divided by 8 ohms, well, that's the resistance of resistor 1, so 1.1 amps current at resistor 1. Repeat the process, 9 volts into 6 ohms, 9 volts into 14 ohms, and on and on and on, so we get all 5 resistors. Then of course we have the current at every resistor. Now we can get power, which is the current at resistor 1 times the voltage at resistor 1. So we have 10 watts at 1. Then same thing, we go 1.5 amps at resistor 2 times 9 volts, 13.5. Same for 3, same for 4. Same methodology, that is. So that's how you calculate the power at every resistor. Then we just take the total current times the total voltage, multiply them out for the total watts, 231. And to check the work, you take the watts dissipated at every resistor, add them together, it should equal 231 as well. So this proves the circuit analysis was done correctly. Thanks for watching this video and have a great day.